So, good evening. I think nobody else will be joining, so I think we can start the session for today. So, am I audible to you? Okay. So, is the screen visible right now? Okay. So, we'll start. So, this is the last session on live problem solving in GATE Metallurgical Engineering. So, and most of your classes, I think, will be ending by 31st January. That is what the instruction we got. So, at the end of Jan, these sessions will stop and there will be no live problem solving sessions in February. So, on that note, this will be our last live session. So, without delay, just let us start solving questions. So, the first question for today is melting point of a metal is 1356 K. When the liquid metal is undercooled to 1256 K, the free energy change for solidification is given as minus 1000 joule per mole raised to minus 1. On the other hand, if the liquid metal is undercooled to another temperature 1200 K, the free energy change has to be found out. So this will be the first question that we'll be solving. So does either of you have an idea on what equation we will be using? That will be an equation connecting temperature, delta G, latent heat, and degree of undercooling. So, in that case, any equation that connects delta G and latent heat can be used for solving this equation. So, can either of you come up with an equation or should I explain? You can take 2 minutes to think if you can come up with an equation from whatever you have prepared so far. So, does either of you know or should I explain? Okay, can you give me the equation, how the equation is? Yes, that is the equation that we'll be using. Delta G is equal to H delta T by Tm. So, in that case, how it will be? So, you might have seen this diagram of delta G versus temperature. So, beyond Tm and after Tm, the delta G values will be changing respectively, and we will be getting this equation that is delta G is equal to H delta T by Tm, where H is the latent heat associated with the process. Here we are dealing with solidification, and then we have delta T, that is the change in temperature, the degree of undercooling, we can say, and Tm is the melting point. Here we know that two temperatures are given and delta G is also given. Therefore, what we do is that we will be keeping H and Tm constant. Then we can say that delta G is directly proportional to delta T. Melting point is a constant and latent heat is also a constant, right? Delta G values will vary and the degree of undercooling also varies. So how do we calculate the degree of undercooling? We have to subtract the given temperatures. That is, first temperature is 1256 Kelvin and second temperature is 1200 Kelvin. So we have to subtract 1256 and 1356 as well as 1200 and 1356. That is how we will be getting the two delta T values, and one delta G value is given, the other delta G value we have to solve. So how it will be? So this will be the relation that we will be using. Delta G1 is given to us, that is minus 1000. Delta T1 we can calculate from the given information. Delta T2 also we can calculate from the given information. So once we know these three quantities, we can solve for delta G2. So can you please try solving? So you can take about 2 minutes, 1.5 minutes, and then I'll go on to the next slide. So this is the basic equation. All you have to do is now find delta T. subtract these two values as well as these two values. Okay. Minus 1560. Is the other person also getting the same answer? Okay. So how it will be? So this is the written explanation. Melting point temperature is given to us. Delta G1 is also given to us. When undercooled to 1256, delta T1 will be 100 kelvins. That is subtracting the melting point and the temperature at which undercooling had taken place. And then again, when undercooled to 1200 Kelvin, delta T2 will be this melting point minus 1200. That is 156 Kelvin. Now we have delta T1, delta T2, and delta G1, and we know we got the relation here that delta G is directly proportional to delta T. On substituting, minus 1000 by delta G2 is equal to 100 by 156, and finally delta G2 will be minus 1560 joule per mole. Is that clear? Yeah. So since it is clear, I think we can move on to the next question. That is, an alloy of an overall composition Xb is equal to zero point 0.7 was equilibrated at temperature T1. Microstructural analysis showed two phases, alpha and beta, and the phase fraction of beta was given to be 0.75. Given that equilibrium composition of beta at T1 is zero point 0.9 as shown in the phase diagram below, the maximum solubility of B in alpha at this temperature is dash. So it's a basic phase diagram related liver rule tire line problem. So here it is given that Xb of 0.75 was equilibrated at temperature T1. Therefore, we can say that the composition of beta at zero point 0.9 and the alloy of zero point 0.7 composition and the alpha will be at the same temperature. So they are asking us to find out what is the fraction that occurs at this point. So I think you can use the tie line or phase diagram. So this is not the actual phase diagram. This is an approximate. This is the assumed phase diagram. Alpha can either be on this side or on this side. This value we don't know. Either it can be greater than zero point 0.7 or it can be less than zero point 0.7. So in that case, how do you solve the tie line problem? So is the question clear? Yeah. So please try to solve. In the examination, provided this diagram is not given to you, based on the information, you will have to draw the diagram by yourself. So please be habituated to that as well. So instead of referring to this diagram and then doing your tie line, try to draw the tie line from this given in text information alone, because it is a possibility that this diagram might not be given to you. So has anybody been able to answer? Point one. So where did you assume? Did you assume alpha to be greater or did you actually get a negative answer first? Okay. So if you are assuming it to be less than zero point 0.7, this will be the diagram that you are planning, right? So in that case, what happens is that once you solve, you will be getting x as minus zero point 0.1. So it's not 1 actually, it's zero point 0.1. So this the equation that you're getting so far? 0.75 is equal to zero point 0.7 minus x by zero point 0.9 minus x. So once you solve it, do you get these steps? Okay, and the next step will be this one. Till this, both are like, is both of you getting the same steps till this one? Yeah, so then what will be x in this case? X will be 0.025 by 0.25, right? And we can see here that there is a minus. So the initial assumption that the alpha fraction is less than zero point 0.7 will be wrong. So the right hand side is negative, which is not valid. Therefore, we have to change the arrangement of the liver rule. So what happened? Instead of assuming alpha here, we have to assume alpha on the other side. So then what will happen? This entire equation we have to just flip. That's all. Like both numerator and denominator we are flipping. Therefore, there won't be any sign change. So then it will come as 0.75 is equal to x minus zero point 0.7 by x minus zero point 0.9. Hence, x will be zero point 0.1. Were you able to identify where you got 1 instead of zero point 0.1? What about Kamish? Is he getting 1 or zero point 0.1? If he's also getting 1, then I might have gone wrong somewhere. Okay. Yeah. So, like, this will be the final answer. So, is it clear to both of you? Point. Yeah. Okay, like we are cross multiplying, like we are taking this to the top. So it will be zero point 0.9 into 0.75 minus 0.75x, right? So what we do is, yeah, so this numerical part we will take to this side. That is zero point 0.7 minus this multiplication. That is 0.075 into zero point 0.9. And here we will be taking, what we will be taking, this x to the other side. So x minus 0.75x will be getting 0.25x. Yeah, and this when you solve, how much would you get? So in case 0.675. So there you will be getting 1. Okay, so this is 1, right? Okay, maybe I've gone wrong. There is no 0 over here, maybe. Yeah, okay. Ah, fine, 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 fine. Yeah, but is the instead of the values, is the concept clear to you? Yeah, so values I might have gone wrong here. Sorry for that. So, like, if you have any doubt with the concept, please let me know. Like, value I might have gone wrong. Yeah. Yeah. So what about Kamish? Is it clear to you? Yeah. Okay. Now we can move on to the next question. Okay. So the critical internal crack length in mm in a steel having K1C of 45 MPa root M to support mode 1 stress of 400 MPa is given by dash. So can anybody tell me what is the equation that we will be using here and what is meant by fracture stress and what is the parameter of that equation known as? Like equation for dash will give us K1C actually. Yes, yes, that one. So what is that parameter called? So sigma, we know it is a stress, right? Like it's something related to stress. So what is that like quantity called? It's related to fracture. So what is it called? Yes. So fracture toughness is basically a material's resistance towards fracture. So whenever we are trying to design a material, it's necessary that we determine the fracture toughness. So fracture toughness, what? How do you define it? It's defined as the plane strain fracture toughness, and it's a measure of resistance to crack extension under linear elastic conditions. And when you might have studied three, you might have studied that there are different modes of fracture, right? So mode one is opening, that is under the tensile force, and mode two will be in plane shear, that is both shear forces will be acting on the same plane, and in mode 3 it will be out of plane shear, so it will be in the opposite direction. So it is given here that it is a mode 1 fracture, right? So mode 1 fracture means that the material cracks open under tensile force. So in that case, now whatever equation that you have just mentioned, K1C is equal to Y sigma root pi into A. So Y we usually don't consider, it's a constant, it's a geometrical factor. Provided it is given to you, you can use. Otherwise, K1C is equal to sigma root of pi into A. And this K1C is given as 45 root m over here, right? And based on that, you have to find the value of A. So can you please try to solve this equation, like question based on this equation? So this will be the equation that you have to use, and this is the given info. Sigma is given to you and the equation of KIC itself is given to you, that is 45 MPa root m. So you have to equate them and find the value of A. Yes, yes, it's correct. And what about the other person? Like, has he mentioned anything in the chat box? Yeah. So basically what is given here is that K1C is equal to Y sigma root of pi into AC. That is equated to what is given to us. And in that case, 400 is also, sigma is given as 400 MPa. So we'll be equating the two, and finally we'll getting the value of AC as 4.03. So in this question, it is mentioned that it is an internal crack. So whenever we are saying the internal crack, we will always be considering the critical temp as 2 times the value of AC. So this is AC, and whatever we use in the equation will be 2 times of this AC. Hence, we will be taking 8.06. Provided in the question it was mentioned that it was an edge crack, the final answer would be 4 mm. So is that clear? Yeah. So this is the next question. Edge dislocation is present in alpha n. Atomic diameter is given and the shear modulus is also given. You have to find the modulus of the Burgess vector as well as the energy associated with the dislocation. So first, what is the type of Burgess vector in alpha n? We know that alpha n is a BCC structural material. So in BCC, what is the type of edge dislocation? Based on that, you will be able to calculate the magnitude of the Burgers vector. So modulus means basically we have to calculate the magnitude. Once you know the type, you can easily calculate. So you have to basically know the type of what is edge dislocation type in BCC, FCC, etc. So do you have an idea on what is the type in BCC? 111. Yes. So so initially what is given to us is a diameter spelling is wrong, I think. No, it's correct. Atomic diameter is given, then we can find the atomic radius. And for BCC, we know this relationship, right? This is the lattice parameter A0 into root 3 is equal to 4 times R. So based on that, what will be the value of A0? So whatever you have told is correct. So before we are going to that, we'll just solve the initial part and keep till the lattice parameter part. So what will be the value of A0? Yeah, 0.29 nanometers. That's correct. So then what we have to do is that for monoatomic FCC it's 110 and for monoatomic BCC it's 111. So we have to take this type as our Burgers vector. So alpha n has a BCC structure and for BCC it will be A by 2 into 111. So once you have A and once you have the type, how would you calculate the magnitude? Yeah. So we have to take A by 2 into root of 1 square plus 1 square plus 1 square. So how would this be? What would be the final answer to this step? So this is the first part of this question. So till the Burgers vector, you have to calculate. So what is the value of B that you're getting? 0.25. Okay, yeah, this is 0.25. Yeah, I think. So there is a mistake. Is the other person also getting 0.25? Okay. So next question is we have to find out the energy that is associated with this dislocation. So what would be the equation that you would use to find energy of a dislocation? Yeah. So the value of G is given as 70 GPa and just now you have calculated the value of B. So what would the energy associated be based on that equation? Half GB square. It is given in gigapascal and please note whatever you found out just now is a nanometer. So after conversion, what will be the answer? So please calculate and let me know. Okay. And the unit will be? This is asked in joules per meter. Okay, fine. So is the other person also getting a same answer? Okay. So 2.2 into 10 power minus 9 joule per meter square. Is it clear? Yeah, this is meter, I think, instead of meter square. Yeah, it's meter. So finally, to the both of these questions, first one will be 0.25 nanometers and the second will be 2.2 into 10 power minus 9 joule per meter. So is this question clear to you? Yeah. So next is okay. The flow stress sigma of an alloy varies with strain rate epsilon dash as sigma is equal to 100 epsilon dash per zero point 0.1 MPa. When the alloy is hot extruded from 10 centimeter to 5 centimeter diameter at a speed of 2 centimeters per second, the flow stress is dash. So four options are given to you. So can you please tell me the equation that we will be using for solving this question? That is, now for flow stress, we have to use the epsilon dot, not epsilon. So we'll be using another equation that uses diameter, speed, and strain rate. Yeah. Yes. So is the other person also having like knowing the same equation? Whatever equation? Yeah. No, ma'am. Okay. So I'll show you. So basically, this is the key thing. Normally, when we are doing equation for that, we'll be seeing in the next question. Usually, when we are talking about flow stress, we will be talking something about sigma is equal to k epsilon power n. That's all. There, true stress and true strain only will be used. But in our case, what happens is that instead of giving us the true stress and strain, here strain rate is being given to us. And when strain rate is being given to us, we will be using another equation for solving the flow stress. And that equation requires that we need to find something known as R, that is the extrusion ratio, as well as the velocity at which the billet is being moved. So how do we find the extrusion ratio? Extrusion ratio is found out using the equation R is equal to initial area by final area. So initial area, so we can say it is being mentioned that the alloy is extruded from 10 centimeter dia to 5 centimeter dia. So based on 10 centimeter, pi d square by 4 we have to take, and final the area will be pi by 4 d square with respect to 5 centimeter. So on solving, what will be you getting as the extrusion ratio? All others will be cancelled. It will be capital D square by small d square. 10 square by 5 square basically. It will be 4, right? Yeah, so you got the extrusion ratio. Now we have to go with what is this equation. So we told that this is the two strain rate and 6V ln R by D, where V is the extrusion velocity, D is the initial dia, and R is the extrusion ratio. We already found out the extrusion ratio as 4, and we have velocity given to us in the question as 2, and 10 we already know initial diameter of the billet. Therefore we will be getting as 1.66 second power minus 1. So once you have got this equation for strain rate, then we have to substitute in what is given to us. Normally epsilon we have to use directly, but in our case instead of epsilon we are using epsilon dot, that is the strain rate. So instead of true strain we are using true strain rate. So this equation for true strain rate you have to memorize. So once you know the equation for true strain rate, you can substitute in what is given to you in the question. This term is actually given to you in question. Sigma is equal to 100 epsilon dot power zero point 0.1. So we have calculated our epsilon dot over here, and once you substitute you will be getting 105.2 MPa. Somebody just joined, I think. Okay. Yeah, is this question clear to you? Yeah, what about Kamish? What did he post? Can I please know? Clear. Yeah, okay. Thank you. Okay. So then I think we can move on to the next question. Next question is the strain hardening behavior of an annealed rod during cold rolling is given by sigma is equal to 700 epsilon power point 2. Though this is what I mentioned. So in the previous question, instead of epsilon, they had given us epsilon dot. So here it is the true strain. There we had to solve using true strain rate. That is why we use the equation 6V ln R by capital D. So here we do not need that equation because we are dealing directly with the true strain alone. Therefore, where sigma is the flow stress at strain epsilon. We have to calculate the flow stress after 50% reduction in area of the anneal rolled on cold rolling. That is the first question. And in the second question, we have to solve if a wire of 5 diameter is drawn from the above cold rod of 10 dia, the drawing stress, neglecting the effect of friction and redundant work, is approximately dash. So initially we have to find out epsilon, then substitute that epsilon to find out sigma. And next question is, there we are not talking about cold rolling. We are then talking about drawing. So what is this stress, the average stress during drawing? So we have to find the value of sigma D. So these are the two questions. So first, can you please try solving the first set? Directly you can find out epsilon, and once you're not able to solve, I'll start explaining. So please take 2 minutes to try to solve this question. Yeah. So what about the other person? Kamesh, are you able to follow? But negative sign. Why is it coming negative? Is the other person getting negative or is it only Kamesh? Okay, so Kamesh, can you please check where the negative sign has come about? Okay, so strain probably, I think. Strain is final minus initial, right? So here it's basically mentioned 50 percentage reduction in area. So first you have to equate volume and then find the relationship for length. So Kamesh, were you able to identify where it went wrong? Strain only. Okay, fine, fine. So basically, during cold rolling, volume remains constant. Area into length is volume, right? So what we do, A0 and AF are the initial and final, L0, LF are the initial and final length respectively. So then what we do is, given there is a 50 percentage reduction, what we can say, area final is equal to area initial by 2. And this area final, we will be substituting area initial by 2. Therefore, we will be getting length final is equal to 2 times of length initial, and hence engineering strain how we can calculate LF minus L0. This is actually L0, okay. This is not 10, this is L0, there is a mistake. LF minus L0 by L0, and this LF you will be substituting 2 times L0, and hence it will come 2 times L0 minus L0 by L0, finally L0 by L0, and engineering strain will be equal to 1. And now that you have got 1, how it will be, we can substitute for true strain. True strain epsilon is equal to ln into 1 plus E. E we got as 1, therefore finally epsilon will be ln 2. And on substituting, sigma is equal to 700 epsilon power zero point 0.2, and it becomes ln 2 power zero point 0.2, and hence it will be 650.523 MPa. So is this question clear to you? This note that this is not 10, this is L0. This is a mistake. Okay, sorry. So is this question clear to you? Yeah, what about Kamish? Is it clear? Okay. Okay, now that you have solved this part of this question, so next is drawing stress. So there is an equation for drawing stress. Does anybody know the equation for drawing stress? Sigma D. Okay. So what about Kamish? Do you know the equation? Okay. So basically, during drawing stress, what how will we be calculating? So before moving to the equation of drawing stress, at least I think you will be able to calculate the initial part up to the true strain part based on this question. So we will discuss sigma d equation later. So are you able to solve till epsilon? At least epsilon can you find out from the first sentence. That is, wire of 5 dia is drawn from above cold roll diameter of 10 So initial diameter was 10, final diameter is 5. If you know these two, you can calculate area 1 and area 2, right? So A0 and AF you have here. So based on that, using the same thing, can you calculate till this part? A0 you can find from what is given. AF also you can find. So at least till that part, can you calculate and let me what is the epsilon value that you are getting? No, epsilon will be different, right? So initial diameter is how much? Initial diameter is 10 Final diameter is 5 So initial area will be pi by 4 into 10 square. This will be pi by 4 into 5 square. So this will be pi by 4 will get cancelled. 100 LF is equal to 25 L0 you will be getting, right? So finally how much LF is equal to 4 L0 you should get. Like area you have to take. Diameters are given to you. You have to substitute in area and find out the relationship between LF and L0. Pi by 4 d square we are substituting. Is it clear? Were you able to identify why you got point values? Like, is it ln4 that you got? Okay, fine, fine. I thought you were talking about the first part. Okay, then it's fine. Here it is ln2. Epsilon you will be getting as ln4 in that case. So, what about Kamesh? Okay, okay. Now till epsilon you have got, right? So, till this part you have got ln epsilon is equal to ln4. Now, we move on to the equation for drawing stress. So basically, this is the equation that we use for drawing stress. Sigma D is equal to Y ln A0 by AF. Now I'll discuss what is Y. A0 by AF you can calculate from what you have calculated previously. 100 by 25 is equal to 4. That part is clear. Now, what is Y? For a material that is exhibiting strain hardening, Y is given by sigma by n plus 1, where n is the strain hardening exponent. Sigma we already know. In the question itself, the equation flow stress is given to us. 700 epsilon power zero point 0.2. Therefore, Y will be equal to 700 epsilon power zero point 0.2 divided by n plus 1. So, this is the equation that you use in case of drawing stress or questions that are related to drawing. So in question, there will be a relation like this given to us. We know that how do we know this particular material is exhibiting strain hardening? Because of this exponent. We have seen that sigma is equal to k epsilon power n for materials exhibiting strain hardening. Hence, we have to take y as sigma by n plus 1, where n is the strain hardening exponent. So this is the equation. Can you substitute in the equation and let me know the answer? Yeah. What about Kamesh? Is he also getting the same answer? Has he posted anything in chat box? Like, have you like learned this equation in theory? Okay, fine, fine. So is it clear? That particular equation have you noted down, Kamish? And are you getting the similar answer? No. Okay. Where are you going wrong? Like, what is your doubt and what is the issue? I'm getting 941. Why is that? Is your substitution going on same lines? Can you please check? 700 ln 4 power zero point 0.2 divided by zero point 0.2 plus 1 ln 4. It's not 700 epsilon the whole power zero point 0.2. Whatever is given to you in the question itself, 700 epsilon power zero point 0.2. 700 is different, epsilon power zero point 0.2 is separate. And then finally ln A0 by AF, that is 4. That is ln 4 here we have, and n plus 1. N is the zero point 0.2 that we are using here. Because this is actually k epsilon power n. Hence it will be zero point 0.2 plus 1. At Subramanian, you got using the same equation, right? Yeah. Okay, fine, fine, fine. So I hope it's clear to both of you. So Subramanian, can you just please dictate the answer that you got again finally? 863. Okay. Okay. Yeah. So this is the final answer. So we got 650 for the first set, and this one you'll be getting it somewhere around 853. So this is all for today, and this will be our last session. So thank you for joining with me for these past sessions, and hope you write the exam very well. And in case you have any particular question, doubts, or something, try to please post in this particular mail ID. I'll be trying to solve them before your examination and send you the answers as soon as possible. So keep preparing well. Practice on your gate calculators. All the very best for your examination. And once your exam is done, if you find time, please let me know how your exams went using the same mail ID. So thank you so much for joining. You both may leave now. Thank you so much. Yeah.